Today we are going to talk about what is called deformable part model, and this is one of the method which has become very popular, and lots of people are using it. The original paper, the journal version of that appeared in PEMI 2010, and it has been cited more than 2,000 times, and it's a pretty comprehensive paper. It's about 20-page PEMI paper, and they have a nice website here you can visit. Code is available. There are different versions of this code. I think they have version 5 now, and it's widely used. So I'm going to try to convey the main idea behind this method. Of course, there are lots of details. One can spend a lot of time. So the main problem is similar to the problem you wrote the last program, human detection. Given an image, we want to detect where is a human. If there are multiple humans, we want to put a window around each of those people. And you did that, and that was based on the HOG, the Latent method. And the performance of that method on the Pascal VOC 2007 dataset, VOC is Visual Object Categorization, which is a complex dataset, is about 12% AP, which is average precision, which is very low, and that was published around 2005. So now main thing is to increase the AP to help improve the performance, and this paper did pretty good contribution to that problem. So AP has gone up from 12 to 27, then 36, and I think latest is about 45% in 2010. So you can even go to 49%, but that's a separate topic. So the origin of the DPM, which is in DPM, has become very common phrase. Everybody will use computer vision. It's so popular, it works so well. So it's DPM again means deformable part model. Okay. So the Latent trick, the algorithm you implemented, uses histogram gradient orientation, or HOG, and does SVM training and sliding window, go through each window and determine whether there's a person or not. So the main new thing, which conceptually, which happened in this DPM work, was to introduce the pictorial structure. When you look at the human is a non-rigid object. It's not fixed, because humans have arms, legs, and torso, and face, and so on, and they move. So what you did in a program was just fix one window, and you're computing the features, HOG, and doing the SVM. So therefore, the humans can appear in different poses, as you see here. And so in this model, so the parts of the humans are also modeled. So that's why it's called deformable part model. And these parts can deform in a way that the distance between parts, or distance between a root or torso to the parts, can change, deform, depending on the pose of the person. Okay, and this was original idea was from this paper in '73, but then Felsenschwab and Nattanaka, there another paper, they used that, and so that's the important point. And essentially, DPM at a high level can be look at whatever you did for the program, the Latent tricks, HOG, and deformable part model, which is in terms of this part structure, then it becomes DPM. And DPM, then what you have is the root filter, which is this one. Up to here you did what you did then. This is exactly the same like here, the program. But now we have these, which are the parts, and typically there are 8 parts. And then also deformation cause, which is shown here, and we'll talk about that. So the example of a DPM is like this, as shown here, a bicycle bicycle has two wheels and all this thing, and the red one show the root filter, which is the global, how the bicycle look like. And it's shown here in terms of the deep, HOG, and these are the part filters, and there are different parts of this, and corresponding to each part there's a deformation cost. So it's like, you're looking at a face, there are eyes, and there's nose and mouth, and these are the springs attached. These are the deformation. The spring attached in this cost can vary depending on your articulation of a face or articulation of the pose, body parts, and so on. Okay, so these are nice slides from one of the author. He was, I think, graduate student at Cornell. Now he's a postdoc at Berkeley. So he gave a tutorial at ICCV, and I borrowed his slides. If you look at this whole space where you have to do trade-off, so one is that you can do the deformable configuration of parts. Other is parts, so this is, parts are not deforming, but the distance between the parts is deforming, so it's a different. And here, the old method where you can model an eye with, one ellipse and circle, and this is really deformation. And there are some, and this is a selection that you do deform, and then you have rigid parts. Then also you learn the sparse, like interest point, the shift points. So they did not use shift point, but the dense, which is HOGs are dense. You do the pyramid and you compute that. And of course, this is a discriminative model as we talk about. The SVM and discriminative, it has positive, negative, discriminate that, find the margin, as compared to generative model where you have probability distribution. And similarly, this is explicit structure, and this is using templates, and will be able to deal with translation scale, because translation you are doing sliding window, and scale is because you're going to do pyramid. Okay, so now in Dalal and Trigg method, you knew that given an image like this, then you find a pyramid and you compute HOG pyramid, and essentially you computed the W from the SVM, and this is HOG at level L, and that W essentially can be looked at as a template, as a filter you apply to the image, because that's what you are multiplying W with the HOG. So the steps are compute the HOG of the whole image at multiple resolution, the pyramid level, then scan the every sub window of each pyramid, apply the non-maximum separation, pick the one which is maximum locally. So yeah. So the now if you look at the detection, maybe you can move closer or something. Maybe sit here, because I should have the yeah. I should have the speaker or something. Okay, just keep reminding me. So now in an image there are lots of possible locations as you went through the scanning window, and many images. If you have 5,000 images, test sets, and you have lots of these windows to classify, and so it is extremely hard, lots of computation, and in a way that you have lots of locations, but there are very few true positive, because in most of places there won't be a person. Okay, so this is the plot, shows you the performance of this HOG-based method, and you have done this. So the precision recall curve. So ideally you want 100% precision, 100% recall. You want somewhere here, but of course it's very hard to get. And these are different versions of these. You can use the kernel SVM, linear SVM, wavelets, features, PCS shift, and all those things. and this is the best performance. We'll give you 75%, and he re-implemented that. It's about 79%, and that is pretty good on the INRIA dataset you used. Okay, but we'll have problem with this kind of person, humans. Okay, because a different pose. So object detection with HOG. Again, a review that HOG is a feature. The linear SVM is a classifier. You take an est image, you extract the HOG features, and then you have a model which you have learned from your SVM, which is a W. W can be treated as also a filter. If W is a vector, but you put back as an image, then it looks like that. This is like a human model. You multiply with that, then you will get something like this, and then you will say if it's a human or not. So it's interesting that in a way, human detection using HOG and SVM can be treated as a template matching. You're basically applying a template, which is very nice. Because the SVM essentially is doing your W multiplied by the feature vector X. Okay, so now why do we want deformable part model? The reason we want the great variation in objects, non-rigid deformation, as I told you, human in different poses, intra-class variability, cars and various sizes, various brands, Ford car compared to Lexus and so on, and viewpoint, they look different, and elimination. So therefore we want to introduce these parts and deformable parts, and so there will be more filters. There will be filter corresponding to each part in addition to the root filter, which is the whole human, whole object. Okay, so it will look like that. So we'll have the red one is the root filter, which is shown here, which is very exactly same as you did in the program. And then these are the part filters, as you see. There's a head filter, there's arm, legs, whatever. And then in addition to that, each of filter we have the deformation model, which says that, well, what is a penalty you will have if the part is displaced from the center location, and these are the weights or cost. So these are circular, elliptical cost. If you are farther away, then you have more cost as compared to closer. So we essentially in DPM we are going to estimate this, we are going to estimate these parts, we are going to estimate these. Okay, so that's the idea. In the HOG we'll just estimating this one. Yes. I mean, so we will say that there is a model which is the parts, and that model can be cars or gates and any object.
What I'm trying to ask is somebody was sitting then very far away, right? And the lower area would be so they would be very far on the bottom, but not necessarily we've added it all up.
Yeah, so all those are training based methods. So whatever training images you will have, it will compute these filters. So other thing we are going to do is that we'll have mixture model. So we will have one model for humans standing up, other model like sitting and so on. You can introduce several different models. There will be different models for different objects. There will be model for a car and model for airplane, which is very different. So all these, if you have many training examples, you can separate them, sitting, standing, and lying, so you can repeat this process. Yes?
How are these models defined? Is there somebody manually saying, okay, for a human, we would divide it like this, or is that actually computed?
Yeah, so you just say that, well, you want, for human, you want eight parts. A priori, you will just define 8 parts and roughly put where they should be. And for the cars, you can have several parts. But the annotation is given at part level. Annotation is given exactly the same you had annotation at the whole human level. So the interesting thing about this is that it's automatically going to identify where the parts are and identify also these weights. Okay? So yeah.
This cost that you're getting, is it relative to what we are assuming it stable cost, which you're doing with the coarse fruit filter? Is it relative to what the coarse is and the coarse fruit filter, the cost?
Yeah, I mean it will be based on that set of training examples you will use. If the other training example is standing up and stable, so it'll be related to that. But if you have mixed up, then it will use that. It's purely training based. Okay, and we'll see more example of that. Okay, so here is the thing. Starting point will be this. So someone say, well, there are these 5 parts, and they will be at a fixed location in all these images, because we don't know, we don't have annotation per image. We say, well, upper part is head and like that, legs and so on. And so we will represent human with several parts, and the position of parts are not fixed, which means model is deformable, and that is the cost thing I showed you. And we will penalize the parts that are far away from where they are supposed to be, and that's a cost, and this will be the cost. Okay, so then what we are going to do, that we will have the coarse root filter, which is the standard HOG, Latent tricks, but we will have high resolution filters for the parts, which are shown here, and deformable models. So model is a root filter F0 and N part models. Okay, so we'll have, this is our model, different filters, F0 to F1, F2, and in human typically you have 8 parts, and then the anchor position, the center of that part, and the deformation DI, which is the 4-dimensional vector. And so Fi is ith part filter, we has anchor position of the ith part relative to the root, and Di deformation parameter for ith part. Okay, so the object hypothesis is that we will do the HOG feature pyramid. You have done that, and we will do the root filter, coarse scale, part filters, finer scale, and this shows you the image, different levels of image, the pyramid, and then this is the HOG pyramid. So the main point here is that given the location of the root, we want to find out where the parts are, and that is the difficult part. Okay, we want to find out the P1, P2, P3 up to Pn n parts, and given where the root is. Okay, and we are going to sum up all those scores of the parts to get the overall score if it's human or not. Yes?
Initially, at the beginning of the lecture, you said that the HOG is on the 12% capture, and then you're saying that the parts require the root, so still at the 12% of catching anything before we can do the parts?
No, we will compute the parts and root simultaneously. So we are going to estimate all those, which will make the difference. So you will see that. Okay, so the score of a hypothesis depend on we'll have the root filter, the whole human. We'll apply that to the HOG. We'll get a response. Then we'll have these part filters, and we are going to talk about how to compute these part filters, which is the main thing. So then we'll take the response of part filter 1, 2, 3, and all the scores we'll add it up. So that is one term about the score that when the root occurs at P0 and the parts occur at P1, P2, P3, and so on. This is score for that. As you saw here, depending on the root, then we are going to find the part where they occur. So that is first term. The filters, these are your HOG, and of course this is at that location, and also your level and so on. So the second term is the main thing, which is important, is the deformation parameters. So di is a vector, and then 5d, which will be a function of the displacement of the part from anchor position, the displacement dxi, dyi, and it will also be a 4-dimensional vector. So I'll take two 4-dimensional vectors, multiply, or find out product, will get a scalar, and that will be the deformation parameter cost, and the B is the standard bias. Every SVM will have that. So this is a data term, and this is a spatial prior, or the deformation cost. So a score of hypothesis Z is depend on this multiplied by this. So beta contains the unknowns. So which has the filters, F0, F1, all the part filters, deformation for part 1, deformation part 2, there are D's, and the bias. So, and then the psi HZ, this is the known. This is the response of the HOG for part filter 0, part filter 1, part filter 2, and all those things. Then 5D, these are also fixed. They are quadratic terms, I'll show you. And the unknown is the beta. Okay, so this is unknown, which we want to compute, and this will be known to be fixed. So that's the basics. Okay, so now what is this deformation cost? So we are going to find the deformation cost of 4-dimensional vector, and initial value will have 0, 0, 1, 1, and then that's a di, and then 5d, which will be a function of dx dy, the displacement from anchor position, will be dx dy dx squared dy squared. So as you see, initially when you take, this will become dx squared plus dy squared, which is the distance from the anchor position. If it is further away, you have more cost. If it is closer, it will be less. So it looks like a circle. But depending on those values, the first two values, all those values change. This can look like an ellipse or some other shape. Okay. So those are your costs. Yeah, it's good. This is a very, very important method, and it's really, really useful. So you want to really understand. Once you understand, you can do lots of things with this. And so then when you take these D5D and DI, whatever you compute, multiply, you can plot these things. Because for given X, Y, you will get these values, and multiply, you will get one value, and the next value, next value. It's like a Gaussian. Remember, you can do the Gaussian, but this is not exponential. This is just a square term. So that's a penalty or deformation costs. Okay. So now let's talk about how you will do detection. So let's say we have trained. We're going to talk about how to do the training, but let's say we have trained this. We have the root filters, we have the part filters, and we have the deformation cost and all this thing. So we want to find out, given a test image, where is the person based on the parts, deformation, and root. So once we understand that, then we'll go actually how we do the training. So which is actually in the reverse direction. So overall score of a root location is computed according to the best possible placement of parts. See, so we want to make sure that we know we are finding the human such that it is confirmed by the parts also, not just only root filter. Because what you did in the program was only root filter. So that's a new thing here. So a score will be that we will look at all possible places where the parts can be. Given that the root is at P0, we want to find out what is the score that there's a human there. So we will look at all possible places where the parts can be part 1, part 2, and so on. We compute that score. Wherever it gives you maximum, we say that's a person. That's where the person should be. Okay? So highest scoring root location define the detections, and we'll do that through a sliding window. And we can do that using dynamic programming generalized distance transform. So see, the idea is that, let's say you have 8 parts. So now, given a root location, there are many possible location part 1 can be, there are many possible location part 2 can be, and all the 8 parts. Now we want to select from those combinations the best part location, root location. So it becomes very combinatorial explosion and lots of combinations. That's a problem. But you can simplify that. You say, well, okay, let's given a location of the root, let's look at all possible places the parts can be, and you compute for the part 1, you compute that for part 2, compute it for part 3, then you sum them up, you will get it. So it will simplify the complexity, and that's the idea of dynamic programming. So in dynamic programming, you take the big problem and break it in sub-problems, like here we are doing. Instead of finding the best location of 8 parts together simultaneously, we want to just look at, say, given a root, what's the best location of part 1? Sub-problem. Given a root, what's the best location of part 2? Sub-problem. So we find those, then we join the results and we get that. And we have to do this sub-problem only once. Otherwise, we have to keep doing all of those together. And that's the idea. And then generalized, distance transform is going to facilitate that, and I'm going to talk about that. Yes?
To come back to this question, you still rely on first finding the root. If you don't find the root, then you don't even start looking for parts.
Yeah, we will simultaneously find all those. I'll show you, just wait. So we'll do the distance transform. So right now we have assumed that here we are doing detection. So magically we have done the training, okay? So we have the root filters, we have the part filters, and we have the deformation costs, everything. We are talking about the detection. So, and we are talking about how we can use distance transform. So what we are going to do, and how can we do quickly, efficiently. So what we have, say, let's look at the response of ith part filter. Okay, so as you know, we will take the HOG level L and apply the part filter to that for the whole thing, get the one image. We will call this RIL, the ith part L level, which you have done. That's pretty simple. Yes? Okay. So now what the distance transform will do, that let's say the root, and we have done for the root also. We have a root filter, we have applied that. So let's say root is located at XY. We're going to look at all possible places, but let's say we pick the XY. Then what we are going to do, we will transform this RIL to DIL, which is a distance transform of that, which is saying that, well, since we know the root at XY, then we want to look at the possible displacement dx dy in the part response, which is shown here, which is from here. And for that possible displacement dx dy, what is the deformation cost? This is the way we have defined. I talked about that. This is a vector, this is a vector. It depends on the deformation dx dy. So we can find this. Now we will take another displacement and find this. Another displacement, we find this. So these are possible displacement dx dy from the anchor position of that part. And whichever give us the maximum score, we'll select that. And that's what we want, because we want to maximize the score. Okay? So just wait, let me finish, then we can come back. So as you remember, the 5D is dx dy, dx square, dy square, which is known. If you know dx dy, how much you want to move, then that's fine. And di, also known, we learned that. Let's assume we have already learned this. then it's very easy. So this is the response of the ith part filter applying to the image, and this is HOG. This is a response of HOG to that filter. Then this operation essentially will give you, so what we are doing, say, let's say this is the location P0 where the root is, then we are looking at the small neighborhood around that, and which is governed by this, and finding all the values of this, whichever give you maximum, we are going to replace that in this. So this will be transformed to this, and it's very simple, just this one line code, you can do that. Okay, it's very easy. And this, we need that, and that's the idea, that you have baked this thing, elegantly, so it's easy to do that. This we will do for every part. We'll do in parallel. Okay? So then we will have something like this. So as you see, we started an image, we apply the root filter, and this is our HOG. These are the HOG maps, and this is twice the resolution. Then we apply it to this, the root filter, we get the response like this. And the twice as the resolution, the part filter, the head is applied here. Next one. So these are these responses. Then on this one, we do the distance transform, using this thing. Okay? So then this will be transformed here, this will be transformed here. Now we can take these, add them up, which is very nice. We can add up, we'll find what is the score of human detection at that point. Because now what we have done, we have combined the response of the root filter, and we have deformed or displaced using the distance transform of the part filters. We have incorporated all the dx and di and all those things. We sum it up, and we find the maximum of that, and that's the human. So which is very nice. So that's your, given the training, this is the way we can do detection very quickly. Now you can ask question.
The question was, you're talking about the displacement, so we're assuming that there's no rotation on the parts.
Yeah, as I say, there's only scaling and the translation. There's no rotation. Okay? So now let's talk about training. So how actually we find these filters, the part filter, root filter, the DI, and all those things. So we are given the training example exactly the same as you were given for the program from India data set. There were bounding boxes on humans, but we don't know where the parts are. There's no annotation of parts. We'll just arbitrarily select those locations, and they'll be fixed for all the images, even though they will be wrong. And we want to discover the right location of parts. And so since we don't know the location of parts in annotation, they are unknown, they are hidden, they are latent. These are latent variables. So that's why this SVM we're going to talk about is latent SVM. So linear SVM, standard SVM, classical SVM. It's a latent SVM. Okay? The classical SVM has only W unknown. That's what we want to compute. Here will be Z, which will be location of parts will be unknown. So that's why it's become more complex, and that's the reason it works very well. Okay. So our aim is to learn model parameters, data, the filters, root filter, part filter 1, part filter 2, part filter N, D1, D2, D3, Dn, deformation, vectors, each is a 4-dimension, and the bias B. So then we are done, that's what we will have. The root filter and little part filters in this, there are little windows here, and the deformation. And we have used these different people, and depending on training you will get this. So latent variables, hidden variable, unknown, are these location of the parts, and position of parts are not given, in the both training and the testing images. The variables that exist but not known in training samples are called latent variables. Okay? The learning algorithm must be able to discover optimal values of latent variables. These are the position of the parts. Okay? So how are we going to do that? So we will have the classifier scores an example X by this, and that's what we have been trying to do. So we will have the Z is possible, is from a set ZX, is the possible places these parts can be, and these are your filters and unknowns, and this is your HOG. So beta is a model parameter, that's what we want to find. Okay? Z is the latent variable. Okay? So ZX is the possible latent values for template, for example X. It can be anywhere. There are lots of possible places we don't know. We want to find out them. So what we are going to do, we'll minimize objective function, which is very similar to the SVM you have learned. Beta is like your W, and even though here now it's not a hyperplane and so on, this is actually filters, which is interesting. There are filter values, the root filter, part filter, all those, but it's a vector. It's a huge vector. Okay, so but that's fine. We can use that as our function which we want to minimize. And this is very similar to what we did. I'm going to explain that. This uses what is called hinge loss instead of just 0-1 loss. But otherwise, this is in a way is regular SVM. Instead of W, we have beta, and this is the same thing. As you remember, the positive yi will be +1, negative yi will be -1, and this is the function will give you, if it is positive, it will be greater than 1, if it is negative, it will be less than 1, and so on. So now we are given the labeled training examples like you had from India data set. Given a bounding box of a person, this is the positive example, so y is 1, and there will be some negative examples, there's no person, which will be -1. That's a standard. Okay, so let's talk about why we want to use this hinge loss. So remember I showed you this slide, so we were up to here, that we want to take this select variable eta I, and we want to make this thing greater than or equal to 1 minus eta I. And if you look at this constraint, this can be written like this: yiw wxi, or that's w transpose xi is actually fxy, and 1 minus eta I. So what we have done, we have multiplied yi, this is your fxi, and then we have rewritten this in terms of that, which is given here also. Instead of w transpose xi, we just put fxi. Now this is equivalent to this, that we want to say the eta I should be maximum of 0 and 1 minus yi multiplied by fxi. Okay, because this one can be found from here. You can bring in this other side, yi 1 minus yi fxi, and you bring in this side, so eta I has to be greater than this, and then we have constrained that eta has to be greater than 0, so we can write down this like that. So it's a maximum of two things, which means it has to be positive. Okay, either 0, or if that second term is more than 0, we'll take that value. So it's another way to write that. Okay, so therefore we will take this thing SVM. Before in your SVM, this is equivalent to this one. So W is same, C is same. Instead of this one, you have just put this one. Now this is unconstrained optimization. There's no constraint. Everything's captured here. Okay. The other thing you did for quadratic programming, which was constrained. So it has this constraint here, and then we are using this one. So now it's unconstrained. So this thing is called loss function. Okay. And so the loss function is this, which is the maximum of 0 or this. Now you remember that this is the margin we are looking for. So we have the blue one and we have the red one, and you want to come up with a margin so that they are separated. And so now if the yi, fi, xi greater than 1, then this will be outside the margin. So whether it's a positive or negative, it will be outside. It's greater than 1. So it will not contribute to this loss function. Okay? So when it's greater than 1, this will become negative, then we'll always pick the 0. When yi of xi is 1, then this is pointed on the margin. Also it will not contribute because it will become 1 minus 1 is 0, so we'll pick the 0 again. Now only time this will contribute when yi of xi is less than 1. So that is that it is actually somewhere in here, and that's the problem, which is less than. So that will violate the constraint, and that will be a problem, and that's what we want to minimize that. So that's called loss function. And this loss function as a name, somebody called Hinge came up with this, and it is a better than 0-1 loss. Okay, so 0-1 loss is the one shown in blue, and which is saying that if the yi of xi is positive, there's no loss. Remember that if the example is a positive case, then yi will be 1 plus 1, and this will be greater than 1, so it will be positive. If the negative example, this will be minus 1, and this will be less than 1, it will be again positive. So these are the all places where we are making the right decision. Because it's a human, you detect as human. It's not a human, you are not detecting as human. That's a right decision. That is the all positive values. And for that, there should not be any loss. Now, when this is less than 0, say minus 1, minus 2, minus 3, which means there's a problem, which means this was positive, but this became negative, which is wrong. And this was negative, this became positive, again it's wrong, which is, false positive and false negative. So in the 0-1 loss, you just say loss for all these cases 1, when there's no loss 0. Now Hinge loss, what it does, which is this one, it is, if it is 1, then the loss is 0, but if it is less than 1, even the negative and so on, so it goes like this. So it is assigning some weight depending on how bad it is. In the other case, it was assigning same weight, constant. So that's why it's better, and it's called Hinge loss. Okay? So that's the idea. So now we'll talk about a little bit about the optimization. I hope I can finish this thing. My phone doesn't work. Okay. So now we have a function. We want to minimize this function. Okay. This is still a standard SVM. It's not. We haven't done anything with the latent SVM. So in SVM, the only thing we have played with the loss function, and you did the other one. You did like this. The constraint, you did this one, constraint minimization using quadratic programming. Now we are doing unconstrained. So now the function you get, as we have talked about before, if this is a function, then this is a local minima, this is global minima, and this kind of function will be difficult to get unique solution. So always we prefer a convex function. So this example of convex function. So if you draw a line joining 2 points, so for this point, then the function, all the points will lie below this line. So that's called convex, like this. Concave is other way. Okay, you learn from physics. So it's easy to minimize a convex function. It's very nice. But if it's not convex, then it's hard. So this is a convex function. This is convex. This is not a convex function. Okay. So now this is convex, and this is not convex. So it's a summation of that. So there are details about this, how to minimize, but since I don't have time, I think I'm going to skip this. Let's go back to our original problem here. But I'll send you the slides. Okay. So let's go back to now. So the idea was about the standard SVM, how you use hinge laws and formulate this problem as the unconstrained problem and solve it using gradient descent. And these slides were taken by Andrew Zisserman's presentation, which is very good. So let's look at, now we are going to talk about latent SVM. The reason it's a latent SVM because we don't know the location of parts. That's a big problem. But we want to use the parts, and there's no annotations. Okay, so latent SVM is a semi-convex. It's not a convex, and so remember that we want to, or beta is what we want to find, but we don't know the z also, where the parts are. So we have two unknowns. Beta is unknown, which is similar to w, which is okay, we can do that in standard SVM. But now we have z is not known, and that we have two unknowns. Positive, then it's not convex, because positive y I leave 1, so it'll become like this. And this is the maximum convex function and the concave function, and it is not the convex. Okay. Now, if we assume that we know the latent value, the position z for this particular example, then it will become convex. Okay, so the latent SVM, the way it works, we will initialize beta using a standard SVM as you have done. So beta means the root filter, the part filters, and the deformation, that whole beta vector. So we want to compute that. And if we know the location of part, then it's just a simple SVM, which is fine. And what we are going to do to start with, we will just fix the location of the parts in all the images, even though they are, one is different like this, we don't care. We'll fix that, which means z will be known. We'll go through the SVM, compute the beta, compute the part filters, work with the root filter, compute the deformation cost, and so on. That'll be initial estimate. Yes? So then we will do iteration, and using the model we learned, the beta, then we are going to look at all the positive examples, the training, and in that we will fix the beta, and which means these filters. Then we will find the z, that given these filters, given these deformation cost, for each positive example, what's the best place we can find the human. And so that's actually a detection. That's what we are doing. Is that right? We are given filters. We want to find where's the best place where the part occurs. We do the distance transform. We do this for all the parts. We have the root score we added up. So that's the detection. So essentially, and that's the reason I covered the detection before the training, and this is that one. Okay, so this is what you are going to do detection. So we found the part filter, root filter, deformation, all these things, assuming the parts are constant in all the examples using standard SVM. Then we can do this. Now we can find the right location of the parts. We'll give you Z. So we fix beta, we find the Z, and we are going to do iteration like that. And that's where it will improve. And that's what this is telling you, that we will, where we were. Okay, here we go. So did I cover this? Yeah, good. Okay, so minimize this objective function, labeled, and all this thing, we covered that. Okay, then let me get there here. So Latent SVM is semi-convex, we went through that, and initialize beta using standard SVM by using the same part location in all the images, iterate, relabel positive example, fix beta, find the best Z for each positive example. Then once we know the positive right Z, then we will fix Z, will find the beta again. Okay, so now the Z will change because we have, using this, we have found the right location for each of the positive example. So therefore, in this step, we are going to use the Z we found. Here the Z was fixed for all the examples. So that's the difference. Now since the Z will be different, so the beta will be different. Beta will be better. And what is beta again? Anybody? Root filter, part filter, deformation, everything. And that's what we want to find. Okay, just hold on 1 second. So then this is what's going to happen. Initially, we will have these parts arbitrary, fixed place. As you see in this first one, second one, head is exactly located in the same place, even though here head is right place, here not, but the same locations and same. So we suppose the position of parts are fixed, each frame, train the part detector using SVM, train SVM classifier, and using the trained SVM, find the optimal part location in each training example. So we are going to do now this thing. And we found the better place for each part. This is very nice. Yes? Good. So now we found the right places. We take that Z, compute the B, and keep going like that. Isn't it amazing? Okay, just hold on 1 second. So now the other thing we are going to do for negative examples. So this is what we did for positive examples. Now negative examples, there can be lots of negative examples. Any window which is not human, you can use a negative example. There are many, so that's a problem. So this is the technique what is called hard negative. So we want to find out what are the hard negative, which is difficult negative, which are the problems, and we want to somehow use them to improve our classifier. Okay? And the idea is that the hard negatives are the ones which are like this, that they give you if this is negative, then this will become positive, which means being on this side, it will become actually other side because it is switching the side. So this is shown here. So see, now this should be on this side, but because these are your positive examples, these are your negative examples. So the negative examples are actually moving to here, and these are the hard negative, because it should be on this side, because these are unfilled circle. Now it became here, which are the filled circle. So they took a jump, somehow the features and so on, actually it becomes, it should be positive, it should be negative, but it became positive all the way other side. And these are called hard negative. And for those hard negative, we will have this condition that this will be greater than 1, or this will be, if yi is -1, it will be greater than 1, or generally we'll have this less than 1. So these are the hard negative, and we will find out, and there can be many hard negatives, we'll find out the ones for which the response is maximum, because this is our response, the beta multiplied by your HOG. And we'll collect those hard negatives and use those to improve our classifier. So a couple more things, then we'll stop. So the other thing, as we mentioned earlier, that one person is standing and person is sitting like that, so it will be difficult to come up with one model which will capture that. So that's why they have introduced mixer model, which can be many components and capture the extreme intra-class variations. And so we will take the training example split in different mixtures, and suppose here's the example of a person, and so the different pose and so on, and this will be one model, and this will be another model. Here the person is sitting. So person detection, we'll use both of the models, which I will give you maximum. We'll say that's the person present. Each of the model will have root filter, part filter, deformation cause. Root filter, part filter, deformation cause. Similarly, it's a bike, and like that. Another one model, this another model. So for these 2007, these are the detection for person. This is the car detection and horse detection, sofa, bottle, cat. And so they competed in 2008 challenge, and out of 20 classes, DPM got first place in 7 classes, second place in 8. And these are the curves. So that is the DPM for the person, and these are the other methods. This is for the bicycle, this is for the bird, and these are the different comparisons. If you use only root, which is your HOG, which you implemented, which is here, but you put parts and all those different variations, and many more things.
What are the different roots? There's like 2 different numbers.
Yeah, so the I think 2 roots, like a 2 mixer model or something. Yeah, mixer model. Yeah, the main thing is that that you can improve a lot if you use 2 roots, parts, and something else. I don't know what is that. So that's it.